We're starting. All right, everybody, welcome to software engineering lecture number 7. We're learning about a DFD. Okay, a DFD stands for data flow diagram. In the previous lecture, we saw system analysis in an object-oriented approach using with UML diagrams, use case and activity diagram. Right, the use case actually in a previous lecture, right? It says a previous. Because we also learned about class diagrams. But now, no, come on. In this lecture, we will see another way to analyze the system using DFD diagrams, which importantly are not part of UML. The kind of diagram that precedes UML. And we're still teaching it because it gives a nice view of a system. The functional analysis approach is a different approach than system analysis. This is functional analysis, not system analysis. It has nothing to do with the first approach studied and object-oriented, which is object-oriented approach. Okay. The purpose of the analysis phase, the goal is to provide a detailed characterization of the new information system. That is to precisely define the execution in the system while referring to the following elements: the computer processes, the inputs, the outputs, and the database. Those are going to be the 4 parts of our diagram: the process, the inputs, the outputs, and the database. The product of this analysis of the analysis phase of the information system will be the basis for the design and implementation of the system. The truth is, originally, the idea of a DFD was that you go to an organization that's currently working and has certain procedures. They have, department of I don't recall, like the money that pays for things, and then you have the ordering department, and then you have all kinds of different departments, and information travels between them, and each people and all the different workers do different things, and it's all done, let's say, without computers. So we want to make a computerized system of version of what they're doing. So we interview them and we find out what each person's doing. And the way that you find out how a system works, or one way, you have a whole system, how do you just figure out how it works? You ask each person, what information do they receive and from whom? What information do they put out and to whom? And what do they do with that information? Essentially, there's information coming in. She said, well, I get order requests and I check the amounts and see that it's within our budget, and then I approve it or don't approve it, and then I hand it off to the requisition department. So we know what information she gets and what information she passes off to the requisition, and what she does. So that's a way of analyzing a system. It's like in Hollywood movies, they say, or in I don't know, Hollywood movies, news programs, they say, if you want to find out, where the crime is going, follow the money.
Follow the money.
Follow the money. So here we're doing follow the information.
I think I saw that in Law and Order.
Yeah, follow the money. If you know where the money is going, and then eventually reaches this guy's hands, so you know that he's in charge. And you have to figure out who came to these hands, then to those hands, and we follow all the way where it goes. So we're doing the same thing, but we're following the information. The products of the analysis phase information system will be at this stage, the software components will be defined. There will be a functional definition. That's what it does. This definition will be the basis for the development of the application software. Okay. A DFD is a graphical means of describing activities and the flow of information between them. Its purpose is to present the activities that the system performs, the incoming outgoing information, as we said. It's a static view. It mainly shows a static picture of a possible information. We really need to see an example quickly. There are 2 types of DFD programs, DFD diagrams. That's interesting. Yeah. There's one called the Gain and Sarson approach, which supports the creation of what we call a flat diagram. When we say flat, you may have heard of that term in databases. You have a flat table. Ever hear of the term flat table as opposed to a relational database? You learned about relational databases?
Yeah, we learned that in database.
But did you learn the alternative?
We haven't gotten our names back to that course yet. Shop our goal and said we will.
Did you learn the alternative? When did you take the course? Semester Olive?
We took it around I think I brought it 4.5 months ago.
Maybe you quite a strong word.
That's unusual. That makes me feel good that I give the grades back quickly.
There's 2 parts for waiting, but for computer science and data.
But the professor hurt his leg in the head, so he can't.
Don't get it.
Well, you know how you know the best way to grade.
How's the best?
You take all the exams, you walk over to a stairs, and you throw them up the stairs. And the ones that reach the highest, you get the 90s.
Is that how you grade?
That's how I grade.
Can I quote you on that?
You got it not right, so the ink doesn't weigh down.
Wait, what?
Oh,
Is that why I got?
What if you change it up? Again, what if you change it up and like goes to the top?
Patrick, if you like a strong
What
one,
if you
you
change it up,
because
goes to the top of
like
the stairs?
somebody
You
said.
don't want to red locks there. Never know
Oh,
what's.
the steps are too high?
Sorry?
The higher they are, the higher grade.
I'm saying it's strong because like the grades were pretty low.
Alright, I'll try to work on it. I'll try to work. I'll work on improving my throwing.
Alright.
What if you start from the top of the stairs?
You heard that one?
That's an interesting idea.
And we also get low rates. We just get low rates.
Quite a lot.
Okay, that was a lighthearted comment. Let us continue. DeMarco approach supports the creation of a hierarchical database, DFD. It's kind of a, and we need to see an example. Let's jump to an example. See, we're gonna talk about it all this time, then we don't need. Well, that was an example. Here, all right, here's an example of. So here's an example of a DFD diagram. You don't have to understand what exactly is here, but you see that there are circles and there are rectangles. The rectangles are databases, which really you should think of as tables in a database, because it could only be one database, but it's tables. This is a particular table, this is another table, and another table. And then there are these circles, which are processes. And then there are these as a box around the whole system, and then on the outside, there are various entities, and those entities are sources of a flow of data. So, for example, a worker could put in some data into this function, and then that function could process the data, maybe change it in some way, and put it into this function. And this function can do something, and eventually it goes to a triangle. A triangle is a real-time item. In other words, like a machine that can receive or give data. For example, we're going to see an example of like a sensor, that receives data, tells you how moist the ground is, whether we need to water the ground, and then that will give us data, and then we'll make a decision based on that, and we'll cause the sprinklers to sprinkle, and that will be another real-time object that will receive the information. Start sprinkling. Anyway, this is a DFD. And when we said there are 2 types, we said is there could be flat and it could be hierarchical. This is, what you're seeing here is flat. See, everything that there is in the whole system is right here. But actually, it's hierarchical also, because we have a double circle here. And a double circle means that that's a complex process which needs another page to explain it. So we then get a hierarchy. In the DFD 0 level, see, you could have in one system where it's hierarchical, then you have a DFD 0 level, and then beneath it you have explanations of what was going on in 0. Let's go back to the slides just to where we had this thing about. So anyway, the one approach is flat, and the other approach called DeMarco is hierarchical. In point of fact, we're not actually going to do it exactly the way DeMarco says to do it, because there's no 100% standard of how to do things. It's not like UML, that's a unified modeling language that everybody agreed upon. It's just certain principles, and you can do a DFD in different ways. So drawing a world map where there are 6 continents, for example, Australia, Europe, America, Antarctica, Asia, Africa. If we draw the whole world in one diagram, no, that's it.
I thought there's 7 North America.
Oh, well, they're connected. Yeah, he considers, this is, I didn't write this.
So it's Asia.
Asia and Europe are connected too. Africa's connected.
Africa's not.
And then after.
Africa's connected, just as a canal.
Well, so America has a kind of a.
But the canal is, that doesn't, it's the
Oh,
same
it counts,
continental,
I can't.
well, that's just, how deep is that? 20 meters? It's not, doesn't count as a separation.
Technically.
It actually has to do with continental shelves. Anyway, if we draw the whole world in one diagram, well, the disadvantage of this is that it will be difficult for us to read and understand everything, right? You can have a globe. If you have a globe, you can see all the continents, but if you want to know like the capital of Queensland in Australia, you might not find it because the map might be too small to show all the details.
I thought it was Adelaide.
Adelaide is the capital of Queensland?
No, Brisbane, my bad. Brisbane, so it's the capital of England, it's capital of Australia. What's the capital of Australia?
Is it Melbourne? Or Sydney, I think it's Sydney.
It is Canberra.
Oh, Canberra,
What is
yeah.
Canberra? Everyone thinks it's Sydney, but
Oh,
it's
it's Canberra, it's good.
where is Canberra? Whoa. Yeah, I'm more of a Perth guy.
So if we prepare a hierarchical, so if you ever buy an atlas is a hierarchical system. Because you maybe have on the first page the whole world, and then it has like a 1 on each continent, a number on each continent. And then you go to that page, and then you see that continent, and then each country, you see England there on the top of the continent, so you can turn a couple more pages to see all that just England. So it's hierarchical in the sense that you can go deeper and deeper into detail, but you still have an overall view. So that's basically what we're going to do with the DFD diagram. The super diagram will contain the continents, but not their content, not everything in them. And then they open a diagram for each continent and so on. It will make it easier to understand. Okay. So that's DeMarco's idea. It's hierarchical. We don't draw the whole system on the same diagram, but there's a hierarchy, meaning that for each breakdown, we go one level lower, and the lower we go in the hierarchy, we find more specific or detailed diagrams. The diagrams, there's always a father for every diagram except for the first diagram, which is the father of all diagrams. Each diagram has either one son or several sons, and a connection is maintained between all the diagrams. Okay, so first of all, what are the parts of the diagram? We already saw it in a quick view. Here we'll see a detailed view. So there are 5 main parts. The circle is a process. We call it a function, but a process that the system performs, marked with an N or a P. Usually a number. The N is a number, and the rectangle denotes a external entity or system, and it's usually marked with an E for entity, and then a number. The N means, when you see a little N next to the E, this means a number. So E1, E2, entity 1, entity 2. And then you have the name of the entity. Like you call it E1, and then you'll call it like manager, or E1 requisition officer. And then this will be a process, be like 2, and the process name, like compute salaries. And then you have these triangles. The triangle, I have an elongated. Well, first we'll do the elongated rectangle. Elongated rectangle is sometimes drawn without the last line, and sometimes with, but it has a little box in here, and it's a D and then a number. And that means the database and or the data table and its number. So you'll have like database 1, and then maybe you'll have in it receipts, the name of the purchase receipts or whatever it is, client information. Whatever information is in that table will be written, the name of the table will be written here. And then you have the triangles. And a triangle with a T is a time entity. Which means that at a certain time, it's like a timer. At 12 o'clock at night, we do a certain process to indicate that a process is done according to a timing event. And then if there's an R in it, it's a real time. If it's the same triangle but with an R in it, it's a real time entity. Now there is a difference between them in the following way. We'll talk about it more, but the T can be only on the left side of the diagram. Why the left side? The left side flows into the system. The right side flows out of the system. You don't update a clock in general. A clock should be a clock. Time. But the R could be on either side. Because like I said with the example of sprinklers and the sensors. Sensors detect dryness of the water, and sprinklers sprinkle. So they're both real-time entities, and they can be either side. And then there's the arrow, and the arrow just shows a flow of data. It doesn't necessarily indicate a causation, but it is showing the flow, where the data is coming from. So a circle can be a single or double, and I already mentioned this. If it's a single, we call it a simple process, and if it's a double, we call it a complex process. Simple, and what does it mean? Complex means, well, there's actually a lot of terminology. The simple one can also be called a base process, a basic process, or primitive process. I don't know why I have basic process twice, but whatever. P for process.
There's either N or P.
Yeah. Yeah, it's a process. So it's a basic process. All these terms are used in the professional literature. I like to call it simple or base process. So a simple or base process means that I'm not going to explain any further what this process does. Here is the name of the process, that's all you need to know. If it's a complex process, then it means I'm going to give you a general title, but I'm going to have to explain more about it. I tend to explain more about it in a lot more detailed tables. There's also the system boundary. Everything that is within the information system will be found in the boundary. For example, people are not part of the information system, which is surprising, and will therefore be outside the boundary. We actually mentioned in the beginning lecture that people are part of an information system because they're a source of information, but they're not part of the system that is going to be developed. We're not going to create people. They're part of the system, but they're not part of the system under development. There's actually a term called that.
Interact.
SUD, system under development. What?
They interact with the system without being part of it.
Well, that's what I'm saying. It's a philosophical question. They are part, we said in the first lecture, they are part of the system. Because they interact with the system, they're part of the system, they provide information for the system. So they're sort of part of the system. But they're not part of the SUD, they're not part of the system under development. We're not developing better people. Everything that does not belong to the information system will be outside the boundaries. So here we're actually going to put the people outside of the boundaries. The input side versus the output side, the left side, as I said, is data coming in, and the right side is the output side, people receiving output from the system. Be on the right side.
Is it outside of the system on the right, or is it
Yes.
other parts of the system could be?
No, outside the system on the. No, you could have theoretically, it'd be confusing, but theoretically you have this arrow pointing to here, and then this arrow pointing to here, and then this one pointing back out. The circles can be anywhere you want in the system. There's no right and left within the system. But outside the system, these are all sources of data, and these are all recipients of data. And there's some details that we can look at this database. For example, if you notice this D1 here, and D1 here, and D2 here. How come we have D1 twice? So you're allowed to have the same table twice, but if you put it a second time, you usually put a slash in the corner here to indicate that it's just a repeat of the same table that was already mentioned earlier. So why is it there? It's simply there to avoid having a line going, straight from here to there, which would be messy. We don't want lines crossing over circles and things like that. So if we want to keep the system easier to read, we may repeat a database table. And here you see that there are 4 simple processes and 1 complex process, which means this is like the state of New Mexico. I'm not going to explain anything more. That's it. That's the state of New Mexico. This one will be maybe Australia. And here I'm going to give you some more details about Australia. So I have a circle of that, a double circle. Remark. The same entity can play both roles. Notice that you have E1 over here and E1 over here. Because it could be that he puts in data and the system does its, processing and clanking and ringing and whistling, and then eventually comes out after some smoke clears for the data that he needs. So he put his data in and he got back his data that he needed. That's one thing. for example, a student may want to enroll in a course, but he also wants to find out what courses he was accepted in. Okay,
With it,
yeah.
take with this. Start.
Okay, guys, we're continuing. Information system analysis. We will see how it performs this analysis by doing functional decomposition and using DeMarco's hierarchical DFD diagrams. Sounds fun. There are two methods for creating a DFD: bottom up and top down. Bottom up means you get all the processes and you start grouping them, and then you say these three processes fall into one category called student management. And these processes fall into another management called like teacher management. And all the things that do with teachers, I'll put here. So first you find out all the processes you want, and then you start grouping them. That would be bottom up. Top down is to say, oh no, I know already that I have management of teachers that I want to do. Now let me figure out all the processes that will be in that. Usually when we talk about an abstract system that we're creating, we usually do top down. But when you have a real system that you're analyzing, you may do bottom up, because you just know all the things that are being done and they're not grouped. And you may come up with a certain way, you just can find out what's being done, and now you have to group if they weren't grouped previously. But when you're creating a system from your head, you probably will do it top down, not bottom up. So top down, you'll take a general thing and you'll break it down into subsystems and more subsystems. Now, the first DFD that you make is called DFD 0, or in Hebrew DFD Ephes. The number of processes in this diagram. Wait, the number of the processes in this diagram. Usually, most of them are complex. In other words, you'll have maybe 6 or 7 processes in your DFD 0. Great, Nachum, can you not talk? It's like here you go. Even though you're back there, you're talking about DFD 0 will have in it processes with numbers, maybe 6 of them, and they're usually most of them are going to be complex because you're not going to be able to explain everything in one diagram. So each of those complex processes will be broken down into other pages. For each complex process, a diagram is opened with its name and its number as the name of the complex process. So in other words, if I have in my DFDFS, I have process 1, 2, 3, and 4, then I'll have DFD 1, which will explain process 1, and I'll have DFD 2, which will explain process 2.
I have a slightly different slides for some reason.
Really?
Yeah, it's got that last one.
Some of them.
Oh wait, the last one you did on in the last line.
Alright.
Sorry.
DFD 0 diagram always contains all the complex processes of the information system. Okay, so here you see an example where we have a DFD 0 and we have all complex things. Management of lecturers, student management, department management, course management, administration, employee management. They all have the word management because that's just the easiest way to think about a general process. And then, what exactly, maybe I'll also add in here databases, what databases each of these use. We'll talk about whether you add databases or not. Later, we'll have to explain each of these ones. If there's a double circle, I must define what it does. Process number 2, which is student management, can be broken down into the following things: registration for courses, student payments, student union, registration for exams, welfare, loans, student loans. We ask the following questions: what can be done with students? In other words, what are the sub-processes related to college students? So diagram 2 would then look like this. A diagram DFD 2 would have 2.1, because inside of 2 now there are processes, and we have to number them. So 2.1, 2.2, 2.3, 2.4, 2.5. And these are all each also complex processes. And one is called registration for courses. Now, registration for courses obviously is complex because there's many steps to register for a course. And my payment student, I don't know. Association, these are bad translations. Association to students Registration, student union, it means student union. Welfare, like loans, registration for exams. Why is the diagram called DFD2? Because it specifies the complex process it specifies the complex process called number 2, found in DFD0. A lot of people make this mistake and they think, oh, DFD0 is the top level, DFD1 is the next level, DFD2 is the best level, 3 is the next level. It's not true. DFD0 is the top level. Underneath it are DFD 1, 2, 3, 4, 5, 6. Underneath those are DFD 1.1, 1.2, 1.3, or 2.2, 2.1, 2.2, 2.3. The names get longer as you go down a level. Why is, does it say there? Why is process 2.1 complex? Well, because registration for courses is going to be complex. It's got a lot of steps. Because it can be broken down. And then we'll find the following steps: checking the registration time, eligibility, is he got all the prerequisites? Is he paid? Is it conflicting with some other course? Is the course full? All those checks I've got to check. Is the course full? If it is, then I don't let it. If it is, like, he's got to pass all these different tests. Does the course overlap with another course he's taking? Okay, and there could be also rules, like if you want to graduate in computer science, you have to take at least one course of this type, one course of that type, and one course of this type. But you can't take 2 of the same type. You know the different names for the course, but they're all in the same category. We have a rule like that. Like you can't just do a degree in computer science where all your courses are the history of computer science, right? You could have all kinds of different histories. Computer science in England during World War II, computer science in one course. You did that, right? You do a degree in business where your whole course is just like history of economics, and not learn actually how to do the math part.
That's economics.
Economics has math. Okay, so we saw that these things can be broken down. Each complex process will have a decomposition to at least 3 processes. In other words, if it's just 2 processes, then better just increase the name. In other words, then it's really simple. It has to be at least 2 subdivisions for each complex process. Creating a DFD diagram of a given system. DFD diagrams of a given system is done in 2 steps. First, do the DFD0, which you could also call a root diagram, and then do functional decomposition of each complex process found in DFD0, and that would be top down. Sorry. So you got to find the main process of the system. Find also the databases and the entities that interact and where the data flows from. How do you locate the main process for an information? Through the organizational structure. That's saying like this: if you have an information system for a college, then you probably already have a department of collecting money from students, a department of assigning them courses, a department, all the different departments that exist. So there's an organizational structure. And now if you're going to make a computerized version of that, well, that's your starting point, is how it's already been divided as in a structural way. Usually the main processes of the organization correspond to the organizational structure. Because that you have a secretary that deals with each topic. So for example, you might have financial information, student information, personnel management. And these are just examples of what would be done in each of those processes, but I think it's relatively obvious. Means for identifying complex and base processes. There are no exact rules to determine whether processes are complex or base. So let's come up with some 3 means of identifying that help. If the system analyst estimates that the process does its logical process, that what the process does can be described in a short verbal description, structured writing, or a flow diagram, then it's basic. That is, if I can do a short flow diagram, then it's basic. If the process cannot be broken down to more than 3 subfunctions, then it's also not complex. If the process is united to many processes, database external entries, then it's probably complex. As if it interacts with many other processes and a lot of databases, then it's probably doing a lot of, it interacts with them, so you gotta decide when does it interact, and what circumstances, so then it's gonna be complicated. How do you perform a functional breakdown of a system? Analyze a complex process means finding the sub-process make up the complex process. You take any complex process that is in DFD 0 and decompose it and make it type. Okay, we said this, it's a little bit repetitive in some of the slides. So here you have a basic structure where you have a DFD 0, and then it's broken into DFD 1, 2, 1, 3, and 4. Why is 2 not in this diagram? Well, good question. Why is 2 in it? The answer is because, well, I would say because it's simple, but then why is DFD 4 here? This tree is not always balanced. The number of decomposition levels does not have to be equal in all directions. I think it's really not, they're not trying to say anything here. But the point is, this is fully explained. This is fully explained. This DFD 3 is not fully explained, and therefore I need DFD 3.3.
I'll put through without one.
I think the idea of this diagram is a little weird. I think the idea of this diagram is to just show things that are complex. All of these things here are complex. This is complex. This is complex, but all of its children are simple, so we don't show them. This one is complex, and most of its children are simple, but one of its children is complex. And that's why DFD 2 is not here, because it's simple. I think that's the
It's
point.
fully explained on DFD.
Yeah, this diagram is right. This is called a tree diagram of all the diagrams. I don't know if you have to do it that way. You could also put simple ones. So, but it's not enough to just make the DFD diagram. You have to have what's called a data dictionary, where you define precisely what is in each table of the database, what each entity's job description is, what the processes do. In other words, you may not have all, like the process may be, remember we said that a simple process could be broken down into a flow chart. That means it has to be explained what it's done. So even a simple, so you'd actually, the processes would be explained in a data dictionary. What is this process called? Register student for course. Maybe I'll define the steps that are in that in a separate place. Even though the DFD will call it a simple process, because it is because let's say it's relatively simple. This does 3 things. So there'll be a process description in a data dictionary. And also what the streams of information are. I can write on the stream, for example, user personal data. But what personal data? Do I want to know his home address or not? What personal data? So that will have to be defined. What is the user personal data in the data dictionary? Right, I might want his email, his phone number. I might also want his home address. I might also want his his nearest of kin. I might want, no, the near, his ID number, well, that's for sure, but I may want like next of kin. In case he's like, let's say an accident happens in the school, we need to notify them. Advantages of the hierarchical diagram approach. It allows you to see the system in a single glance without getting into too much detail. And then it allows you to also see detail when you want to see detail. The approach enables the coordinated work of several work teams. Once the main diagram has been defined, the rest of the work can be done simultaneously. In other words, I can define the main thing and I say, oh, you figure out all the you analyze the system that deals with students, all the student stuff. You analyze the system that deals with all the teacher stuff. And then I can break up the work. For each basic process, we will be asked which data flows enter it for its operation, which data flows leave it. Right, we need data flows. If there's no data flows in a process, then it's not a process. Process must have data flow. That's why it's called a DFD, data flow diagram. The data flows entering the process can be from an entity or from a database or from another process. Data streams that go out to a process can be to an entity. We go out to from a process. Can be to an entity or to a database or another process. We will identify where information flows come from, where they go to. This will thus we will discover the participating. So here you see that diagram again. And you see, we're gonna say anything about this? Yeah, what do you see here? See the data flow from entity 3 into complex process 3. And then he writes to this database, and 4 reads from the database. 4 also writes to the database. Is D3 more than D1 is twice. And you see lots of people are writing to this complex process. Data is going into it. So you see, he must be doing lots of different things because he's getting all kinds of different data. Now there's a rule I'll tell you like this. When do you put a database in a diagram? You don't always put, like if this is a DFD 0, you might not have all the databases in DFD 0. Why not? Because if there's a database that, let's say, only 4 only is the only one to talk to this database. Nobody else talks to this database, just process 4, and 4 is complex. So then I may as well, when I do the deep dive into 4, then I'll show the database who's writing to it, reading to it. In other words, in any diagram, a database must be written to and read from by 2 different processes. Now you say, well, wait a second. In this diagram, but that's exactly what I have here. Only he's the only one writing to it. Answer is no, it's not a mistake. Why is it not a mistake? Because this is D1, and there's also D1 over here. So other people are writing to it. So this is allowed. But if this would be called D4, it would be a mistake. Because if it's D4 and he's the only one writing to D4, then it shouldn't be here. Even if he's writing and reading to it, then he's still self-contained. So it shouldn't be here.
But if he's basically what bigger?
If it's basic, yeah, then, and he's the only one, I mean, it's also unlikely, I guess it's possible. He writes, yeah, it's basic. At a certain point, I'll have to show it, so yeah. Why would he, yeah, we'll think about that. Basically, the rule is that a database should have 1 reader and 1 writer, and they usually, I mean, it could be the same person, but it usually should be a different process. Let's see. So here's DFD 0, here's DFD 1 and DFD 3. Now let's look at that. DFD 1, who does he write to? He writes to database 1 and database 2. He also reads from database 1. So if we go into DFD 1, we see he's writing to database 1 and reading from database 1 and writing to database 2. That's what we saw over here. He was writing to database 2. He's not reading from database 2 because 3 is reading from it. But wait a second. We also see that he is writing. Oh, this is 0, sorry. We also see that he's writing to database 4. And there was no database 4 over here. Why not? Because it's internal. This process is writing to it, this process is reading from it. But nobody else is. So therefore it's internal to DFD1, and therefore I only see it in DFD1. Everything else matches. We see the entities. Now, what does this mean? This little 2 here. This means, well, if you saw over here in the DFD 0, we saw that 1 sends data to 2. 1 sends data to 2. But so now when we explain 1, we have to explain which internal process is the one to send to 2. So we put it to 2. Why is 2 outside of the square?
So his perspective, process 1's perspective.
Exactly. From process 1's perspective, it's external entity. He's not part, this is now a system. And this system, from that system's perspective, 2 is external. Everything else, I think we explained. What about over here? Also here you see D5, which didn't exist before. But that's okay because he's writing, he's reading. You should never have a database that's only written to or only read from. It has to be dual flow. 3.1, 3.2, 3.3, 3.4. And notice that in DFD three, there is a 3.3, which is itself complex, which we'll have to explain what it does. Anyway, all this matches to here. We saw that DFD three writes to 4. You see, there's one write to 4. But if we look at it, we see that there are 2 writes to 4. 3.2 writes to 4, and also 3.4 writes to 4. That's fine. Now, we're not going to write 2 arrows in DFD 0, just because there's 2 different people inside. But in the overview, we're saying that people in 3 write to 4. We don't know how many people. When we look at the details, we see that 2 people are actually writing to 4. Okay. And here's DFD 4, and notice that we have to say that here we just said that they're writing to 4 and they're writing to 4. We didn't say which part of 4. But when we look at 4, we see that Stavka 3.4 wrote to 4.3, and 3.2 wrote to 4.1. So we're showing the detail from the perspective of this process where he got it from. See, it's interesting. I do have a question though. I mean, it works this way, but why did we write 4? If 3.2 is writing to 4.1, then why don't we write 4.1 over here? But why does it care over here? We got to show it somewhere, but you don't need to show it twice. So apparently we show it from the input side, but you see what I'm saying? Theoretically, it could be that we'd write 4.2 over here. Or 4.1, sorry. We write 4.1 over here. And then over here, we can just write 3. And we know which one it is.
It makes sense.
Makes sense the way they did it.
Well, because you need to, like, if it was a getter, then you just need to prepare, process 3 just needs to prepare the data to be gotten by somebody, and 4 doesn't matter who it is specifically. But for input, it does matter exactly who's giving you that. Like, and what's being given.
Okay, I hear you saying.
Well, you don't really.
You're right. In other words, from my perspective of writing the system, I just need to send it just 4. I don't care if you change, if 4 changes and all of a sudden it's 4.9 that wants it. I don't care. I wrote the same function. The data is there. But from this perspective, I need to know I need to specify which data parameters I want. Okay, good. So that makes sense. But I still couldn't figure it out if I didn't do it. I could, but it makes sense to write it this way. Okay, rules of hierarchical decomposition. The law of information conservation. Every database and external entity related to a complex process will also appear in the child diagram of that process. In other words, if I have here, if I see process 1 and he writes database 2, then when I go in DFD 1, I better see DFD 2 over here. I can't skip it. If I saw it here, then I've got to see it. That's what he said. So that means every database related to a complex will appear in the detailed version of that. An external entity will not appear in the child diagram if it was not related to the complex process in the parent diagram. In other words, you can't invent new recipients of data or new givers of data that you didn't see before. In other words, in this diagram, I see that entity 1 and 2 go to 1. When I explain process 1, I better not have that entity 7 is also writing to it. In the detailed version here, I can't have all of a sudden a new entity here on either side. That's what the second rule says. An external entity will not appear in the child diagram if it was not related to the complex in the parent diagram. It is possible to decompose a complex external entity into sub-entities in the child diagram. Right. We could have, like, it goes to worker. And then in the detail, I'll explain which kinds of workers it goes to. And then I would have entity like E4, which would be worker. And then I would have E4.1, which would be a part-time worker, any 4.2, which would be full-time worker. I could have two different, I'd have to label them like that. But I know that there's subcategories of entity, of external entity 4. A new database will appear for the first time when it is shared by at least two processes. At least one updates it and one reads from it. Now, there's gonna be 6 processes, but one has to do the update at least, and one has to read.
So if one process is reading from one database, then we don't put it in.
No, we do. It doesn't say separate processes. It just says it has to be a process that writes, and a process that reads. I don't know. But at least 2, you're right, at least 2 processes, yeah, that's what I'm saying. You don't really have a database that just, that's what you were asking me about this before. Do you have a database that just, I write to it, and then I read from it?
Why does it?
Then it's internal to, what, I don't really.
I mean, if I add DFD.
If I'm writing to it and I'm reading to it, then I'm probably a complex process, right? And then when I go into the, so I won't write it in this, when I go into the detailed explanation of this process, then I'll show which parts of me write to it and which parts of me read to it. So I have 2 different processes.
Open space.
A basic process won't do a read and a write. That, by definition, it's complex. That's the answer. Understand?
I mean,
If I'm just a reading and a writing, when am I reading, when am I writing, I gotta explain that, so it's already complex. That's the point. If I am doing reading and writing, then if process 1 is writing to the database 1 and reading to the database 1, then process 1 by definition is complex, and I'll have to have process 1.1, and he's the one that writes, and process 1.6 is the one that reads. And I'll explain how, and then I'll only show that database when I show the details of process 1.
So if hypothetically on 0, there was a basic process that just read, even though later on it'll get written to,
Well,
like at the lower levels it gets written to.
by who?
Okay, fine.
Then by what?
And if it's just reading, then no, you don't put it in at all.
Again, if it's self-contained within a process, then I don't show it. But then that process by definition is complex, and I'll show it when I. If there's a database that's self-contained within a process, then by definition that process is complex. And then I'll show the reader and writer when I detail it. That's what we have to say. Data entered into a complex process must, in the decomposition, appear at the entry of one of the processes derived from the complex process. Just like we saw, if process 1 gets data, then I can process in the definition of process 1, I have to show that 1.3 is the one that's getting the data. So more rules. Elements of a DFD are the process, external entity, database, time entity, real-time entity, and information flow. We will learn laws apply to each. A process can be basic or complex. Each process in the DFD is given a unique identifier. Each process has an ID, therefore, different processes do not receive the same number. Each process is given a unique number, very repetitive. A complex process are usually given nouns, and basic processes are sentences, imperative sentences, like compute wage. That will be a simple process, but like manage salaries is a noun. Salary management is a noun. There will be between 3 and 7 processes in each diagram. You can't have 2 in a diagram, and you should have more than 7. Be careful not to go into too much detail in the DFT. If we have reached a process that is clear from its name what it does, then don't break it down any further. Do not mark a loop in a process like that. In other words, don't show the process then really does, recalculates it. Let's say if the process, in order to compute some number, has to get a loop, you don't say that information flows from the process to itself.
Every variable.
Every
Variable. It's doing an operation, get it in the variable, and doing something else with it. It's in and out.
You must not create a pit process. What do we mean by a pit process? It has no output. Process 2 here in this diagram. What does it do? It just gets data and then it's a pit. It's a dead. It's like Yamamelach. Water flows in, but doesn't flow out. By the way, if you think about it, just as much evaporation is happening in the Kinneret as in the Dead Sea. Why is the Dead Sea salty and the Kinneret fresh? Just as much evaporation. Because no water is going out of the lake. So the salt flows out as it flows in. And the
There's a lot of
Kinneret,
salt under the Kinneret though.
there is salt, yeah, it could
And
be,
it's a perfect amount of water, and if there's any less salt will pop up and destroy it.
what will pop up?
Salt deposits under the ground. I heard this from like a podcast.
Yeah, it could be even salty water, I think that. Which is lighter, salt water or fresh water? I don't know. But one of them is lighter and therefore you can have a situation where there's a lake. With with a layer of fresh and a layer of salt, or the other way around.
That's crazy.
And then if you shake off all the fresh water, then all of a sudden the salt will be revealed.
And I'll back it.
Yeah, that's what somebody was saying. A friend of mine wrote a book actually about. Why it won't work to refill the Dead Sea with salt water from the Mediterranean. He said because. Yeah, I think that's what he said, is that salt water, when it comes in from the sea, will be lighter than than the other. Right, it must be that it's heavier, right?
No,
We
it's
float
like-
better in the Dead Sea. Why do we float better? Because salt is thicker than regular water, so it pushes us up more. Imagine it would be super thick.
Seawater is less dense.
So seawater is less dense, so it'll float on top and it won't mix. So we'll actually just convert the Dead Sea into a regular sea.
Wait, that's sick. Then you would sink halfway to the salt layer. And it'd be like a cup between the.
No, but if the layer is
The layer-
20 meters, then you wouldn't.
I'm
If we
saying,
put in 20 meters, the point is, if we put in 20 meters of salt water from the Mediterranean.
garbage. You could also make it, you could do that, if you did it like that, then you'd have like a layer, like garbage, like it'll drop in.
Walk over there.
And it'll all just like float right in the middle of the lake.
A certain density of garbage would get stuck there, yeah.
If you just leave a meat to that, then it could be like crazy ocean.
And you
Just
just
what?
mix in the
If you
water.
leave- Let's do like a meter of soup and it's hard to drown, but it's still fun, like absorb it.
Well, that's the thing, no, they could put in 10 meters of Mediterranean water, and then it would be a sea like any other sea.
If you put a meat in, so
Yeah, that
like
would
you
drown
can,
it.
you can like swim and stuff, but you still start to drown.
Right, I see what you're saying, you're right, you keep can't go deeper, but you can drown in a meter of water.
I mean, you can drown anyway if you try hard enough.
We also just mix in the salt water earlier, up the Jordan. That's
Yeah, they
why
have
it's
to-
more soluble,
They have to do something, yeah, I don't know.
or you just.
I don't know exactly. He was just a spoil sport. Ruining the plans of other people.
Is anyone actually playing that?
They were planning, they had some ideas they wanted to do with Jordan. And then put a hydroelectric plant there. It's problematic. Anyway, okay, so what do we have here? You can't have a pit process. You see that's a pit process? It just goes there. Process B has one data stream entering it, but no stream leaving it. This is an error. What about external entities? Users can be employees of the organization or parties outside of the organization or relationship with the system, right? You can be an internal or external party. A user is not part of the software, obviously. He will appear therefore outside of the diagram. And as we said, on the right, if giving, no. On the left, if receiving output, no, this is backwards, right? That's a mistake there in the diagram, in the slide there. He will appear outside the diagram boundary on the right if giving input, no.
From the system's getting that, it's input on the.
If given input. And on the left, if the system is receiving output from him, whatever,
User's output is input.
whatever, the point is the way I said it. He's on the left if he's pushing data in, and he's on the right if he's receiving data. A user is not necessarily the operator of the system, but the person who is the source of the data flow. The user is the one who needs the system's assistance. So, like the example that I like to think about for this is when if I go to the librarian and check out a book, and I tell her, I want this book, and she types in, say, what's your name? And I tell her, and then she types in, then who's putting that information in? The answer is I am. She's just the method for me, I am the source of the data, she's not inventing my name. I know my name, I am giving her my name. And I am giving, you know, so I am the source of that information. So so we actually would put, even if the child never, at the library, never touches the system. He is still gonna be labeled in the system, in the DFD, as the source of the information or about whom the book is being given. Right, the real user, not the operator. The name of the entity is not the name of a person, but the name of the role. Right, so you wouldn't write like Martha Granite, you would write child, or whatever. Or resident. An external entity therefore represents a type of user who provides data to the information system or to whom information is transferred from the system. Therefore, it will be necessary to design appropriate interfaces. I don't know why API exactly, but some kind of UI. Some kind of UI or API for another system. You wouldn't need another API, right? If you have another system interacting with my system, then I need to give him that system a way of programming my system. So I need an API. An external entity is identified by the letter E, any unique number. It is possible to group entities that are common denominator into complex entities. So you hear, that's what I said, E1, and then we have E1.1 and E1.2. We have client, and then we have. I never heard of this word, kamunai, but means like retail. I think it must mean retail client, and sitonai means that I have heard of. That means wholesale. Sitonai, shuk sitonai means the wholesale market.
Okay, you're gonna need.
I know some Hebrew. In the child diagram, it is possible to decompose the customer entity. Exactly. So when we explain in one, we just call them E1. But when we explain one, and we explain that there's 1.4 or 1.7, then we explain which exact entities are in this. It's kind of like inheritance, but we don't draw an inheritance tree.
We don't show they're complex either.
And we don't show if they're complex. Exactly. There's no way to indicate that it's complex. I mean, yeah. Because it is an inheritance relationship, and therefore client is correct. Whatever, yeah, we don't show inheritance. Okay. Explanation of the rules for databases. A database is a storage place, obviously. And the data is going to be needed in the future. Each database is identified by D. When a database is in data DFD 0, or in a database that is a node in the hierarchy of the tree, node meaning that it has children, it should be associated with at least one process that updates it, another process that extracts it. So here you see you have to have one that writes and one that reads. If you don't have that, then you can't show the database. And you'll show it when you do the detailed showing. Writing, updating to the database means like adding or changing or canceling data. Reading is like searching. Okay. Updating a database requires searching for the record we want to update. But there is no need to specify this in a separate process. In other words, I can say I'm updating. I don't have to say that the update first requires to find the item. Examples of reading, retrieving from a database. Retrieve all relevant jobs for each person who comes to an interview. Retrieving the grade of a particular student in a particular course. Writing. Examples of writing. Student address. Calculation of student grade. Anything else that changes data. That's an interesting system to think about, actually, is like a unemployment office system. Where you have actually I had a group that did that, something similar to that last semester. In other words, people come and then you tell them which jobs are available. They're relevant for their resumes. Database component rules. A database can only be associated with processes. This law applies not only to a buffer, but to every arrow in the DFD. There will always be a process at the end of the arrow. In other words, I can't have this example where the entity writes to a database is incorrect. You have to write to a process, and the process writes to a database. Or this, the database can't write to another database. When using a database with the same name and the same ID number more than once, you put this diagonal line. We said that. See how the D1 has a diagonal line. D1 appears twice, but the second time it has a diagonal line. External database, a database of another information system. An internet database. It could be that I update information from some other database on the internet or from the IRS. You know, I connect to their database to verify that the tax ID exists, right? I want to he told me his tax ID number is this. I have to see if the IRS recognizes it. An external database from which the database is extracted will be drawn outside the boundaries on either the left or the right. How do you decide if a database is outside the boundary of the system? Any database that we do not intend to design, because it already exists presumably, will be outside. An external database is any system that the systems analyzes is not currently building, not the SUD, system under development. But our system interfaces with it. Now to our time entity rules. Yeah.
So that if we've got something that writes to the database, something that reads to the database, then we don't need to specify in a separate process updating when you're searching for the records. Does that mean that we're gonna?
I think it's the opposite. You don't specify searching when you're updating.
Right, sorry, so we don't specify searching. Does that mean that there is no other process, or we don't need to mention it because we use the one that?
You'll have a process called update, but you won't have a process called search.
Right, so if we have something that update.
Search is
That's writing,
what?
that's writing, right? And then so the search for it to update, do we
You're not
then use,
gonna mention it.
not gonna mention the reasons.
A time entity is intended for performing batch activities. You know, when we say batch activities, we mean every night at midnight, we do a set of procedures. We back up this system, we copy this system to there, we verify that the numbers are correct. Whatever we do it once a night or twice a night, whatever time, that's called doing things in batch. We collect up a bunch of things to do and then we do them all. And we do it at an off-peak hours. Not at the user's initiative, but at the system's initiative at a predetermined time. At time T, entity T will not appear on the right, as I said before. You never give information to a T. You only, a T triggers something, so a T gives information. It is now 12 o'clock, do this thing. The time can be at the end of every day, for backups at the end of the month, produce a report. At a certain date, the 10th of the month to maybe give people their salaries. Okay. Time entity rule, here you see that the time entity is on the left, and we write on the line the activation date. In other words, nightly, weekly, every day, every week on every Wednesday at 3 o'clock. When it is a basic process, then the time entity is numbered. For example, T1. On the arrow, we will write when the process will be activated. When there's a complex process, then the entity is not numbered. On the arrow, we write the defining string. In other words, we just write activation date. So you see here, the complex one, we just write the word activation date. But in the detailed explanation, we're going to write when is the activation date at the end of every day. So actually in the DFD 0 or wherever you see the complex process, you're not going to write when it happens, but you are going to write the words activation date. Now we talk about real-time entities. Real-time entities can be on the right or the left. They can be sensors. A real-time entity is also indicated by a triangle but marked with the R. A real-time entity can appear on the right or the left side. So here you see a real-time entity on the right and the left, and this is, for example, for detecting dryness of the soil, and this is to start the watering system. And then we check various factors here. You see, we're actually going to talk about this, but what does this say? It says like this. The real-time entity gives me a reading of the moisture level. Guys in the back, I hear you from all the way over here. Still hear you. Okay. Moisture level is being read, and then we say. We accept the levels and then we check, or either do one of these two things. Either the measurement of the moisture is low. And there is enough water. And then I will. If it's dry and I have water in the tank, then I will start watering. But if it's moist. Or it's not moist, but there's no water, then I will go to stop water. So if I'm running out of water or the soil has become saturated, I will stop. So the or means don't do both of these steps. Only one of these processes will happen after this process. Right? Either one. So I write an or here. And I write it with this line. Okay. Fine. Notice that I don't say, I mean, why? This is the process which deals with stopping the water. This is the process which deals with starting the water. And either way, they communicate with the system that actually turns on the water. You wouldn't want both of these lines to be going directly to the triangle. Because then the triangle would have to have some kind of logic in it, but the triangle's not supposed to have logic in it. Okay, rules for information data streams. Going through all the different parts. Data flows is represented by an arrow, okay. We call it a data element, the thing that's written on top of it. For each data flow, the data passing on it must appear, except for data flows that go out to and enter the database. So a data flow between processes has to have the data element. What is the information? I guess if it's going to why don't you need it if it's going to a table? Because then it's kind of obvious whatever the table is. If the table is student information, then we know what data is going there. It's student information data. The data flow doesn't have to be unique because it could appear multiple times. That same information is going around. The identification of the data flow is done using the component at both ends. In other words, I could talk about user information going from process 1.1 to 1.6, as opposed to user information going from 1.1 to 1.5. I can identify, even though it's the same name, I can still identify which one I'm talking about if I want to talk about one, so by referring to the endpoints. Complex data flow versus basic data flow. Complex data flow is information flow in which the data is not specified exactly, but the data is given a title. For example, user details, without specifying which details exactly. Complex information flow will usually appear between two complex processes as an external entity, or a data store, or an entity. A basic flow is a data flow in which the flowing information is written in detail, such as ID number, purchase confirmation. A basic data stream will usually appear between two basic processes and an external entity, either a database or entrance to a basic process. There's no special symbol for it to differentiate them. But sometimes you'll see more detail or less detail, and it should be that the less detail would be with the complex processes. So here you have report data. Produce a report for registration for courses. And he reads from the registration courses database, and he produces the report, and the report goes to the student. Student wants to produce a course registration report. The data the student wants to see are the number, the lecturer, the points, the name of the course, when is it given, which semester, how many hours, what days of the week it is. Details of the fields will appear in the table of the data dictionary. In other words, I'll have a data dictionary which will tell me what is a report. Like what is a I don't know, it's called a registration report. You can have a double-headed arrow, double-headed arrow for basic process. It's not possible to have a two-sided arrow pointing to a basic process. So the first picture on the upper left is wrong, is invalid. Because it must, but two must by definition be complex, because I need to explain when does he write and when does he read. But I could have the bottom left, where DFD 0 has a complex process, writing to D1 and reading. And then I'll explain later. And then the explanation is over on the right, where you have 2.1 writes and two other processes read. So double-headed can only be by a complex logically. Let's refer to the following DFD 0, 2 to 3. The flow is called complex flow. Why? Why is that a complex flow? Because it's going between two complex items. We have to specify exactly where it's going. Suppose 2.3 triggers process 2, maybe it's really 2.3 going to 3.7. How would we show the fact that 2.3 activates process 3.7? Well, the answer is like we saw before. I'll say 2.3 goes to 3.7, and I'll also say 2.3 goes to 3.7. In each one of them, I can do it. What we saw before is different. We saw before is that I only had this one, and over here I left it as 3. All right, so let's take a break here.
All right, Minha. Gulam.
Zoom recording, I'll share. Okay. Let's refer to the following diagram here. DF0 has a simple process going to a complex process. And given that process 2 activates process 3.7, question, where will the connector be and what will its number be? Second case, let's refer to this diagram where we have a complex one going to a simple one. Given that process 2.3 activates 3, where will the connector be and what will its number be? In general, this question should be asked whenever there's a complex flow between two processes. So the answer is in case 1, a complex process receiving data flow from a basic process, right? That's what we have here, complex receiving from a basic. In the child diagram of the complex, so over here, I'll show 3.7 with a line coming into it from 2. Obviously. And over here, in the basic one, when I show the 2.3 over here, I'll show the 2.3 going to 3. That's pretty obvious.
Question.
That's the question. Case 2, a complex process supplying data to a basic process. In the child diagram of the complex process, a circle process will appear outside the boundary on the right side of the diagram, showing the data flow from the particular subprocess to the higher level on the right side. Is that right?
Going out.
Why on the right side? Oh yeah, we'll see a 3 on the right side, and we'll see a flow going to that 3 on the right side. Okay. Trigger, wait, so did we skip anything? Wait, did we skip this? What? Yeah, we did this.
Yeah, we did.
We skipped this.
No results.
So we did this. Okay, so we call that the connector. In other words, it connects between two different diagrams in that way. Each process can be triggered by an external, so the trigger to run a process. So end of the month, and here this is a trigger and this is a trigger. Each process can be triggered by an external entity or by a time entity or by both. For example, the generate report process can be activated 2 ways, as you see here. That's like a trigger, and it's interesting. This is not necessarily a data flow. You see, because he's just a trigger. We're calling that a trigger. He's just saying do the problem, he's not giving you any. He has all his data from databases. The logic in a DFD diagram are simply a static picture of the data flow. However, it is possible to introduce some logic because there could be 2 flows and only one of them occurs, like we saw with the OR. That's what we're about to talk. The data flow relationship between processes indicating that one process flows in the other. Mark or and in the relationship. So you can say it'll do either one of these, and then you have to explain when it does each. Or if you do a line like, or you can write and then it does both. After completion of process one, both 2 and 3 will be done. When we have one process from which more than one stream comes out, and we do not specify any relationship, then the meaning is and. That's logical. In other words, if I don't write or, it's presumed to be and because I'm 2 lines coming out, so do them both. Now, the data goes as a flow from both of them.
In every circumstance.
Yeah. And that's the rule. Maybe you could try to think of an exception, but I don't think there is.
No.
Okay, you could also have and or going like this, but in this case, it's the opposite. In this case, it's if I specify or, then it means only one of them. And if I specify and, it means both of them. What does that mean, both of them? It means process one can be triggered can only be triggered if both process 1 and 2 request for it. For example, process 1 requires 2 data streams in order to perform its task. It can only do its data when it has the names of the workers and their salaries. Then it can compute the report. It needs both of those flows. If I don't specify anything, then what's the default? Then it's or. Because basically what I'm saying is a line says, if this data comes in, do this. And I don't care if there's another line that says if this data comes in, do this. So if there's no specification, then or is applied. That's the opposite of the other example, but it makes sense. It's just logical.
So you would actually write in an or on this, if you wanted to show that there were.
You could write an or, but it would be unnecessary. No, it's just repetitive. If you write or, it's the same thing as if you write nothing.
What if it's both?
What do you mean it's both?
I mean, what if both trigger?
Then you write in.
You don't think both on an or relationship, both trigger, or both could trigger in my diagram. I'm sorry.
That's exactly what it means. So then you don't have to write. What I'm saying is like this. If you write and, then it's clear. If you write or, then it's clear. If you write nothing, then we presume it's or.
So having an or is redundant.
Yes. But once we have an or and an and, we allow you to use them for clarity's sake. Okay, that's enough for the slides. You're gonna have a